Welcome everyone. In this video, I will explain the concept of inverse Laplace transforms. Let us begin with the definition. If the Laplace transform of a function f of t is f of s, then f of t is called the inverse Laplace transform of f of s. That is, if L of f of t is equal to f of s, then L inverse of f of s is equal to f of t. So only when the Laplace transform of a function exists, we will write L of f of t is equal to f of s. So similarly, if the Laplace of a function is existing, we can find the L inverse, which is given by L inverse of f of s is equal to f of t. Let us look into the standard results. I will write the results for Laplace as well as inverse Laplace. If one remembers the formula for Laplace transform, it is very easy to remember for inverse Laplace too. So, Laplace transform of a constant 1 is equal to 1 by s. So, we can write L inverse of the function 1 by s is equal to 1. Laplace of the function e power at is equal to 1 by s minus a. This will imply the inverse Laplace of 1 by s minus a is equal to e power at. L of e power minus at is 1 by s plus a. So this will imply L inverse of 1 by s plus a is e power minus at. Laplace transform of t power n equal to n factorial by s power n plus 1. So this will imply the Laplace inverse of n factorial by s power n plus 1 is equal to t power n. Laplace transform of sin at is a divided by s square plus a square. This will imply inverse Laplace of a by s square plus a square is sin at. Next one, Laplace of cos at is equal to s by s square plus a square. This will imply the inverse Laplace of s by s square plus a square is cos at. Laplace of sin hyperbolic at is equal to a by s square minus a square, which in turn implies L inverse of a by s square minus a square is equal to sin hyperbolic at. Laplace transform of cos h at is equal to s by s square minus a square, which implies inverse Laplace of s by s square minus a square is cos hyperbolic at. Remember, this a is a constant and s is the variable. So all the answers for inverse Laplace will always be in form of the function t. Let us see the linear property. L inverse of a into f of s plus or minus b into g of s is equal to a times L inverse of f of s plus or minus b times L inverse of g of s, a and b being the constants. So now next we shall see the first shifting theorem. I have written the first shifting theorem for Laplace as well as the inverse Laplace. First let us see for Laplace transforms. So if the Laplace transform of a function f of t exists, we write L of f of t is equal to f of s. Then L of e power at into f of t is equal to Laplace of f of t, but the variable s gets shifted to s minus a. L of f of t is nothing but f of s being shifted to s minus a. So f of s becomes f of s minus a. So the variable gets shifted here. Similarly, likewise, we will see for the inverse Laplace. If L inverse of f of s is equal to f of t, then L inverse of f of s minus a is equal to e power at times f of t. F of t is nothing but L inverse of f of s. And also L inverse of f of s plus a will get equal to e power minus at into L inverse of f of s. These are the two shifting properties that we see. Now based on these standard results and the shifting theorem, we will do some problems. Now let us work out few problems. I have listed few here. To begin with the first one, L inverse of 1 by s square plus 1 by s plus 4 by 1 by s square plus 4 plus s by s squared minus 9. I have applied the linear property in the first step. That is, individually I have applied inverse Laplace for each term and then applying the inverse Laplace for the first term. It is in the form of L inverse of n factorial by s power n plus 1. So here n takes the value 1. So n factorial by s power n plus 1 gives t power n, so t power 1. Coming to the next term, this is in the form of 1 by s plus a. So the inverse Laplace is e power minus at, a is minus 4. A is 4. Plus going to the next term, this is in the form of L inverse of a by s square plus a square. A is 2. Here a is missing in the numerator. So we shall divide that by a. And we will write it as half sine at, a is 2. Then the last term, s by s square minus a square, a takes the value 3. So this is cos hyperbolic 3t. This completes the first problem. We shall solve the remaining likewise. Now the second problem, we will find inverse Laplace for s square minus 3s plus 4 divided by s cube. Now when we have terms like this, I will try to split the numerator and write it as equal to L inverse of s square by s cube, applying the linear property, minus 3 times L inverse of s by s cube plus 4 times L inverse of 1 by s cube. Cancelling or dividing this, I can write it and by L inverse of 1 by s minus 3 times L inverse of 1 by s square plus 4 times L inverse of 1 by s cube. By formula, L inverse of 1 by s is 1 minus 3. L inverse of 1 by s square is t plus 4 times L inverse of n factorial by s power n plus 1. We see that here n takes the value 2, n plus 1. So n plus 1 is 3. But that n is missing here. So we shall try to divide that n which is missing. So n takes the value 2. So I will divide it by 2 and write it as t square. In simplified form, I can write 1 minus 3t plus 2t square. The third problem, L inverse of 3s plus 5 by s square plus 9. I will again apply the linear property first. So 3 times L inverse of s by s square plus 9. I am splitting the numerator, plus 5 times L inverse of 1 by s square plus 9. We know by formula L inverse of s by s square plus a square is cos at. Here a takes the value 3. So cos 3t plus 5 times L inverse of a by s square plus a square. Here again a takes the value 3. But a is missing here. So we will divide it by that a. A value is 3. 5 by 3 sine 3t. So very simple problem. The next problem, L inverse of s divided by a square s square plus b square. Now if you see in the denominator, there is a coefficient of s square which is a constant. Always let us have the coefficient of s square to remain 1. So I will try to take this constant outside and I will rewrite this as 1 by a square has been taken outside. So L inverse of s divided by s square plus b square by a square. Since the constant has gone outside, we get s square plus b square by a square. Now this is equal to 1 by a square L inverse of s by s square plus b by a the whole square. It is in the form of s by s square plus a square. By formula it is 1 by a square. S by s square plus a square will give you cos whatever constant is here. So cos b by a times t. So this completes the fourth problem. Let us look into the next one. Fifth one, L inverse of 1 by s minus 3 the whole power 5. Now if you see here, it's not a single variable s. We see that s is being shifted as s minus 3. So first shifting theorem has been applied here. So when the first shifting theorem is applied, what we do is we will take the exponential out. If it is negative here, we will write it as positive. E power 3t L inverse of the function becomes 1 by s power 5. We have taken the shifting outside, so s minus 3 will give e power 3t and the remaining will become s power 5. So e power 3t times 1 by s power 5. It is in the form of n factorial divided by s power n plus 1. So n takes the value 4. We need to divide that 4 factorial and write it as t power 4. We can leave this as 4 factorial and this is the answer. Now the sixth problem, we'll try to find the inverse Laplace for s plus 3 divided by s square minus 4s plus 13. Now if we look at the denominator is a quadratic and this is not a perfect square. So I will try to make the denominator a perfect square. So I can rewrite this as L inverse of s plus 3 divided by s minus 2 the whole square minus 4 plus 13. So the next step, this becomes L inverse of s plus 3 divided by s minus 2 the whole square plus 9. Now if you see, the denominator is in the form of s minus 2 but the numerator is in the form of s plus 3. I need both the numerator and denominator in the same form. So what I'll try to do is, I'll try to add and subtract a 2 in the numerator and rewrite this as L inverse of s minus 2 plus 2 and then this 3 as such divided by s minus 2 the whole square plus 9. Now applying the linear property, I can write this as L inverse of s minus 2 divided by s minus 2 the whole square plus 9. 2 plus 3 is 5. So plus 5 times L inverse of 1 divided by s minus 2 the whole square plus 9. Now if you see, the variable s has been shifted as s minus 2. We need to apply the first shifting theorem and write this as e power 2t L inverse of s by s square plus 9 plus 5 times e power 2t L inverse of 1 by s square plus 9. So by formula, L inverse of s by s square plus a square, here a takes the value 3, is written as cos 3t plus 5 e power 2t. This is in the form of L inverse of a by s square plus a square. A takes the value 3. A is missing here, so we will divide that a where a is 3 and this is sin 3t. So this completes the sixth problem. Now as practice problem, I will give you few. You can work it on your own. So practice problems. First one, finding L inverse of 1 by s minus 3 plus 1 by s plus s by s squared minus 4. Second, finding L inverse of s minus a divided by s minus a the whole square minus b square. And thirdly, finding L inverse of 3s minus 2 divided by s square minus 4s plus 20. You can try these as practice.